Hello, welcome back. So in the last lecture, we saw how the transfer function of a system can be used to characterize the response of a system to periodic sinusoidal inputs. And we saw that the gain and the lag of the response can very well be defined by the norm and angle of the sinusoidal transfer function calculated at a specific frequency. So today I will be talking about a specific kind of notation or visualization of this aspect called Bode plot. But before that, let's see how we can a couple of examples how a visualization or representing this information in graph can be helpful. So in one example, let's focus on the topic of system identification. For instance, you have in this case a car that somebody has given to you, and you want to know what are the characteristics of the suspension of the car. One thing you can do is to put your car on a platform and oscillate the platform with some sinusoidal input with known frequencies and measure the output, the oscillation of the body of the car. And by comparing the amplitude and the phase lag, you can start to construct such plots. For instance, you can see when you oscillate very slowly, you have some relationship between the output and input. That gain may increase at some time and start to decrease at higher frequencies. Similarly, if you have the lag, you can see at the beginning both the input and output, the wheels and the car move together. So you have relatively a small lag between the two, but as the time increases, the body starts to fall behind. Something like that. And then through these measurements, you can try to fit a model that kind of follows your measurement, and using these fitted models you can start to construct the transfer function that describes this suspension of the car. So that's one idea in system identification, that you can use the frequency response to try to construct the transfer function through a frequency analysis. The other example could be in the domain of design. The most useful application is a filter design, but from a more mechanical perspective, you can imagine you want to design a power steering system. The goal here is to have your power steering system in a way that at higher frequencies, for instance, when you are driving on a highway, you want the shaking of the wheels due to the contact with the road is filtered out, and you don't want to feel it at the steering wheel. So in this case, when the input is the vibration of the wheel and the output is the rotation of the steering wheel, at high frequencies, you want to have relatively small gain. So you want your system to dampen out those vibration input from the tires. But when you are actively trying to steer, you want to receive this force feedback from the wheel, so you don't feel disconnected from the car. And this steering feel is very important both in terms of safety and satisfaction in driving. So at lower frequencies, you want to be able to feel all the forces that coming from the tires into the hand. So you want to be able to have a relatively high gain, and ideally up to a certain frequency and then drop. So this is another case that you can use frequency information to design your system, how to behave the way you want. And having this representation of the gain and omega relationship is useful. So these are a couple of examples of how you might use frequency analysis. So you see I plotted, this is not a good line. Usually we don't have that. This is better. So you see I started plotting. So these graphical representations are very powerful in describing how the system behaves under a variety of inputs. And that is what we do using the plot that is named Bode plot. So a Bode plot is exactly this. So in a Bode plot, we plot two things, sometimes underneath each other. On one hand, on the horizontal axis, we plot the values of input frequency, so these are omega. And on the y-axis, we often, on one of them, we plot the gain. So this is the gain plot. And the other one is the lag plot, or phase shift. And we saw that the gain is, how do I do this compactly? Gain is the norm of this g of j omega, the norm of the sinusoidal transfer function, and lag is the angle of this value. One thing to mention here is that we are often working with very large ranges of frequency. So anything from close to 0 all the way to kilohertz, and depending on the application, megahertz. So representing this very, very large range in a linear scale is not very useful. So often what we do, instead of working with omega in a linear form, this axis is in a log scale. So we have 0.1, 1, 10, 100, 1000, and so on. So we plot the x-axis in a logarithmic scale. Same here. This is 0.1, 1, 10, 100, 1000. Wait, why do I have one more? Anyways, 1000, and so on. Similarly, well, let's start with lag. Often we just look at the angle of g of j omega, and for the systems we work with, this angle often changes from maybe a few hundred degrees to minus a few hundred degrees, so that's not a very large range. So we stick with this, either plot this in degrees or radians. Degrees is more common. But for the gain, again, the system, this gain shows very varying ranges of values. And to accommodate that and visually represent this nicely in one graph, so that not everything is compact in one region, instead of plotting g of norm of g of j omega, we usually plot the log of g of j omega. And it is more customary to, well, this one has usually the lag is plotted in degrees. The gain is, if you plot it this way, it is, the unit is Bell, named after Graham Bell, who was working on telephone. Was it telephone? Yes. Named after him. But for the reason I'll explain soon, we usually plot 20 log of norm of G of J omega, and that would give us the unit decibel, 1/10 of what a bell. So this is Bode plot, and usually for the simple systems we work with, look like something like this. For instance, a second order system, and something like that for the lag. I'll give you examples how we can plot these simply. But before that, let's quickly look at this, because I think it could be useful to get a little more detail. So what we are plotting is, so norm of this G of J omega is amplitude of output over amplitude of input. What we are practically doing here, instead of plotting norm of just G of J omega, we are plotting G of J omega squared, which is how do I write this? Let's put it this way, which is going to be, instead of amp, I just write A of output squared over A of input squared. And we work with the squares because they represent power. So the power of a signal is proportional to the square of the amplitudes. And if I take log of this, so, and then I plot log of that in Bode plot, not exactly log of G of J omega, but we are practically plotting log of G of J omega squared, norm of G of J omega squared, and using the properties of log, that one is 2 times log of norm of G of J omega. So this is what has the unit of Bell. But it is usually customary to multiply both sides by, well, multiply by 10 and work with the unit of decibel, 1/10 of that. So that's why we plot 20 log of G of J omega, which has the unit decibel. So that's why we work with that, and why it has the unit of decibel. So Bode plot, in a sense, is not anything interesting. This is something we kind of saw before, that we were plotting the gain and lag as a function of input frequency, the gain and lag of the response as a function of the input frequency. And Let me see if I'm missing anything here. No. Okay, yep. So the only specific aspect of Bode plot are the specific way that we plot them. Other than that, Bode plot is nothing fancy and special on its own. Okay, let's do an example. A very simple example of a first order system. So I have g of s equals 1 over tau s plus 1. Just a first order system with time constant tau. From here, this sinusoidal transfer function g of j omega is 1 over tau j omega plus 1. And I can compute the norm of g of j omega, which is 1 over norm of this. Let me write it down. Tau omega j plus 1, which is 1 over square root of 1 plus tau squared omega squared, and phase of g of j omega equals phase of the top part 0 minus phase of the denominator, which is tan inverse of tau omega over 1, the imaginary divided by real. So this one is minus tan inverse of tau omega. Okay, so this is just me trying to construct the gain and lag of this transfer function, this system, the first order system. Now let's see. I want to plot, let's start with gain. I want to plot 20 log of gain. So let's write it down. 20 log of g of j omega. I just calculated it, so it's 20 log of 1 over square root 1 plus t squared plus omega, no, t squared times omega squared. And properties of the log of 1 divided by something is minus log of that, so it's minus 20 log of, and by the way, this is log with base 10. It's not the natural log, it is base 10 log. Just remember that. Okay, where was I? Log of square root of 1 plus tau squared omega squared. I could actually combine everything in one step. So this is log of 1 plus tau squared omega squared to the power minus half. So I could do that in one step, but now this one, let me write it. Oh no, it's good. This is to the power half, so I can bring down the half, so it's minus 10 log of 1 plus tau squared omega squared. So that's good enough. Now the question is, do I try to plot it here? Do I have space? No, let me finish the analytical part. So that is this, and the lag g of j omega, the angle Do I need to do anything with that? Not really. No, actually not. So let's see if I can fit everything here. So, no, this takes space. I need it. I need to use every space I have. So, let's now plot this. Remember, I want to plot it in log scale. Log scale that. I plot this, and I want to plot that. So, usually it is, we can break this plotting problem into a couple of phases. One is at very low frequencies, where omega is small, maybe non-zero, but close to zero, very small. So when omega is very small, my gain, this one is approximately 0, so I have minus 10 log of 1. So my gain plot, or gain, this is approximately 0. This is not exactly this gain, but that gain in the log form. And my lag is, when omega is very small, tangent inverse of almost 0, something that is almost 0, is also 0. So I'm going to try to plot them here. So this is going to be my gain plot, and this is omega, this is gain, this is lag. So at very omegas, like, I don't know, very small, 0.01, and it's smaller, my gain is 0. So it is something like this. And my lag is also 0. I'm going to draw it here. So at very small values, my plot looks like this, 0 and 0. Conversely, at very large omega, so omega is much bigger than, to have a comparable value, 1 over tau. So let's see what happens in this case. My gain, which I have here, so this term when omega is very large is going to dominate. And what I have is, wait a minute, am I missing something? No, we're good. So my gain is going to be approximately minus 10 log of tau squared omega squared. And again, I can break this, not that, equal, which is equal to minus 20 log of omega plus or minus 20 log of tau. I hope you can see it. I don't think so, but I wrote here minus 20 log of tau. And remember, I'm plotting as a function of log of omega. So this is essentially minus some mx plus b, where x is the horizontal thing I'm plotting. It's something like that. So what I have in a log scale of log omega, I'll have a line with the slope of minus 20. So at very large omegas, I have a line that is dropping minus 20 decibel, what we call per decade. So as this omega increases tenfold, this log omega increases by 1. So when I go from, I don't know, 100, go to 1,000, go to 10,000. So at each of these steps, I drop 20 decibel. And somewhere in the middle is a little fuzzy. So usually if we want to approximate, I know it's going to be like this. So it must somehow in the middle curve like so. So that is an approximate way to plot these gain plots. Let's look at the lag also. So lag. My lag is T omega. So as omega is very large, so I'm looking at tan inverse of essentially infinity, or a very large number. And if you remember from inverse tan, at pi equals 2, tan becomes infinity, and I have this negative of that, so it starts to decrease, and at very large values I have minus 90 degrees. And again, somewhere in the middle, these two have to merge onto each other. Maybe this is 100, 1,000, and so on. Okay, this is the Bode plot of the first order system. I wish I had just a little bit more time to finish something, but that's fine. Do I want to do it here? So maybe it is good. No, let me clean up the board and redraw these two over there, and I'll continue. Okay. So I just redrew the same Bode plots for the first order systems. So at low frequencies, there is zero gain in the scale of 20 log, and as omega increases, eventually the gain starts to decrease at the rate of 20 decibels at every 10-folding of omega. And similarly, the lag starts at 0, which makes sense if the frequency of oscillations is very slow. The first order system can follow it almost perfectly, so it doesn't lag behind. But very quickly, as the frequency increases, the response starts to fall behind, until eventually at large frequencies, the lag will be 90 degrees, and the response will lag by 90 degrees. So one thing you notice, I have now scaled things according to the time constant of the system, just to make it a little more concrete. So one thing I want to mention here, very important and useful terminology, is the bandwidth, the concept of bandwidth. Bandwidth. This shows up in many different contexts. For instance, the internet speed, often referred to as bandwidth, that's different. This bandwidth is defined as the frequency at which response gain or gain of the response falls 20 decibels. So it starts from 0. 0, remember, this is in 20 log scale. So 0 means g of j omega equals 1. That is, the amplitude of the output is exactly the same as amplitude of the input. So when that value drops to 20%, at that frequency we say the system, that is the bandwidth of the system. Essentially an indicator of at what frequencies does the system, the output of the system, at what frequency the output of the system is significantly smaller than the amplitude of the input. So let's calculate that for our first order system. I'm just going to rewrite what we had for this equation. It was minus 20, what was it, 20 log of the square root of 1 plus, yes, plus tau squared omega squared. So this was that line. And we want to see where this one equals minus 20. So solving for that, so log of square root of 1 plus tau squared omega squared equals 1. Or remember, yes, so this is a half because square root is distinct to power 1/2. So 1/2 log of 1 plus tau squared omega squared equals 1. Or log of 1 plus tau squared omega squared equals 2. Or I can raise both sides, raise 10 to the power of both sides. So this time this is become 1 plus tau squared omega equals 10 to the power 2, which equals 100. So tau squared omega squared equals 99, approximately 10, or omega squared, or let's do omega. Omega equals 99 squared over tau, which approximately is 10 over tau. So that's why I plotted here. So that is the bandwidth approximately. The true bandwidth is 99 over tau, but approximately 10 over tau. So whatever tau is, tau, remember, was the time constant of the system. For instance, 2 seconds. So 10 over 2 seconds is the frequency at which the output amplitude will drop by 20 decibel. All right, so that is a quick example of Bode plot. A few more remarks. Let me write a more, I don't know what to call it, a remark or a general case, some comments. So in a general condition, my g of s can be written as some s minus z1 times s minus z2 dot s minus p1 s minus p2 dot. So these are the zeros and poles of the system. So from here, g of j omega, the sinusoidal transfer function, just substituting s for j omega, or j omega for s, j omega minus z1 times j omega minus z2 j omega minus p1 j omega minus p2 So that is my sinusoidal transfer function. And what I need to do is calculate the amplitude or the norm and angle of that complex number. So norm of g of j omega equals, so norm of these multiplications and divisions is the norm of individual numbers multiplied and divided by themselves, or so essentially this j omega minus z1 times j omega minus z2 times dot 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 j omega minus p1 j omega minus p2 dot dot dot. And what I really want to find in this case is 20. So for that, 20 log of norm of g of j omega is 20 log of that, log of j omega minus z1 plus 20 log of j omega minus z2 plus dot 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 minus 20 log of j omega minus p1 minus 20 log of j omega minus p2. These are all norms. Norm minus dot dot dot. So let's look at this for a bit. So when omega is very small, approximately 0, what we have is called DC gain. DC gain. Remember DC and AC current or voltage. DC was the flat, so when omega is close to 0, that is our DC condition. That's why it is called DC gain. So substituting omega to 0, essentially what we have, the gain, 20 log of norm of g of j omega is equal to, I'm not going to write it in this form, let's write it on that form, just 20 log of norm of z1, norm of z2, divided by p1, p2, So the DC gain, or maybe I could add another constant term here, which would carry over to another, to be a constant over here. But essentially what happens is at very low frequencies, the gain can be determined by knowing where the poles and zeros of the systems are. Sometimes useful when omega is very large, or omega is not very large, large enough. Let me break this down into two conditions. So if my j omega is bigger than any of these zi's, so this could be different between the values of z. So what happens is, for instance, for the first one, if j omega is much bigger in size than z1, so it's going to dominate and z1 becomes negligible. And what I have is that term is going to be 20 log of just j omega, and this is added to, so this is an addition to the total value. So essentially after omega is bigger compared to every 0, we add 20 decibel per decade to gain. So the gain starts to have larger slopes every time we go past 1 0. The slope will increase by 20 decibel per decade. Similarly, if we look at the poles, if j omega is bigger than any of the poles, so for instance this one, j omega will dominate the whole term, so P1 will be negligible. What I have is minus 20 log of j omega, and well, I can drop j omega because this is just a complex number with only imaginary parts, so let me drop these. And this means after I have passed large enough value compared to every pole, my slope in my plot reduce 20 decibel per decade, reduce this from gain. Reduce, that doesn't make sense. The gain will drop 20 decibel per decade after every pole. So that's what this nonsensical sentence means. So that's that. So let me quickly again, I'm running out of space. I have similar amount to write down here, and I want to plot. Okay, give me 1 second. I'll erase this part. I keep that. I'll be back. Okay, I cleaned this part. So let's visually show what happened here. So imagine I have a bunch of zeros and poles. What is happening is I start from some DC gain, whatever it could be. Imagine at some point I have a 0. Sometime after that, I will have 20 decibel per decade added to the slope of my line. And this can increase. And maybe I pass another 0. So after that, I will have now, this is 20. I'll have another 20 added. So that would be 40. So after some large enough frequency, after the 2, I'll have another 20 added, so 40 decibel per decade will be the slope of my line. Imagine then this continues, I have a pole, and if I pass that pole, that would subtract 20 from my slope, so I'm back at 20, maybe add, this is another pole. So after that, I'll have a slope of 0, and maybe other poles I start to have negative, subtract another 20 from it. So if this is another pole, now it becomes minus 20, and so on. So what this means, kind of a very useful practical application of this, is that you can look at your large enough omegas. Let me extend the line. So imagine at very large values, I have finally reached a slope that is minus 60 decibel per decade. Just looking at the slope at higher frequencies, I can immediately know that order of denominator is three order bigger than numerator. So just by looking at this slope, I can know what is the difference between the numerator polynomial and denominator polynomial of a system. So that's useful. And the same argument can roughly be used to kind of construct a rough shape of the gain plot, although nobody, I think, really plot these by hands these days. You can type in Bode in MATLAB and it gives you that. But nonetheless, the intuition is useful. What does a slope of minus 20 decibel per decade mean? If you have a first order system, you know, because you only have one pole, you are bound to have minus 20 decibel per decade. Or for a second order system, it's minus 40 decibel per decade at large omegas. So these are useful intuition that you can have about relating the properties of the plot to the properties of the system. Okay, that was the gain. Let's quickly look at the lag also. So here I have lag, the angle of g of j omega. So my g of j omega looks like that. And again, I have this multiplication and divisions of a bunch of terms. So in terms of angle, it's going to be angle of j omega minus z1 plus angle of angle of j omega minus z2 plus dot 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 minus angle of j omega minus p1 minus angle of angle of j omega minus p2 minus dot dot dot. And using a similar set of arguments, when omega is very small, it is a little tricky. So there are a few conditions. Either my zeros and poles are real numbers, so substituting omega equal almost 0, I'm left with a bunch of real numbers that have angle equals 0. Some of these poles and zeros are complex conjugates also, which means the angle of those, one is positive, the other one is negative, they also cancel out. So you're usually left with something either 0, g of j omega is either 0 or a multiplication of pi over 2, and this one needs a little bit of attention. So in case either the zeros or the pole, any of the zeros or poles are identically 0, so 0 imaginary and 0 real part, the poles are 0. In those cases, however small omega would be, is still, well, imagine this z doesn't exist, it's 0. So j omega is always going to be either positive 90 degrees or negative 90 degrees. So depending on how many zeros or poles. It can be 1, 2, 3 if it's the number of zeros at 0, or the other way, minus 90 degrees, minus 180 degrees if you have poles at 0. So at omega small values, you have k, which is in this case number of zeros at origin minus number of poles at origin. So that could be a little, it takes a bit time, so feel free to think about it. Omega, when omega is large, similar to what we did here. So when we compare to a 0, so any of these terms, when, where is it? This one. When any of these terms is dominating the numbers z1, so what I have, so it's going to be angle of j omega approximately, which is 90 degrees. Maybe I could write this as k times 90, because so I have everything in degrees. K times 90 degrees. Okay, that's better. So after we pass each 0, we lead by 90 degrees. So it's add some lead, which, by the way, isn't really a physical condition. We cannot have a system predicting the output, predicting the input. Is it? I think what I said is correct, but I'm not too sure. Anyways, take it with a grain of salt. And similarly, if omega is bigger, is dominating any of the other poles, for instance this one, so what I will have is for that term approximately minus some j omega, and this is minus 90 degrees. So after I pass one pole, so I'll have some lag. Some lag is added to the response. The response starts to lag 90 degrees behind the input after the input frequency passes a certain value. And I can again look at it this way. So for instance, if I start with zeros, but order is by no means in this order, so I start with possibly some plus or minus multiplier of 90 degrees. Maybe after getting bigger than some zeros, I will have a lead of another 90 degrees. And maybe after passing another pole, I'm back 90 degrees. Maybe I have another pole. After that, I'm now back to exactly following the input, and so on. Usually we end up with a lag that is a regular physical system. You will always have a lag, and knowing again how much lag we have at the end of, at very large omegas, again can tell us about the order of the system and the difference between numerator and denominator polynomials in the transfer function. Okay, so that is all analytical and intuition I have for the transfer function. The only thing remains is see it in action, that how we can really simply use MATLAB to construct these. So let's see. So this is just a quick example of what we can do with MATLAB. So here I have defined a transfer function using the function TF in MATLAB. It just made up arbitrary transfer function. I don't really know what system this transfer function represents, but the order of the denominator is just one order higher than the numerator. So from here we can expect to see that at very large omegas, and by the way, the function to plot the Bode plot is Bode. So you can do Bode of this system that I defined using transfer function. So it has a DC gain of roughly, I don't know, 40 minus 40 something decibels. The output increases, and at roughly 1 radians per second, it resonates. Actually, the output is going to be bigger than the input. And in the end, at large omegas, it is dropping with roughly 20 decibel per every decade. So if I go from 10 to the power 1 to 10 to the power 2, so from roughly here to here, I drop approximately, or not approximately, in this case it should be very close to 20 decibels. And similarly, because the order of denominator is 3, numerator is 2, I expect to reach minus 90 degrees lag at the large omegas, which is the case. So what happened? What did I do? What happened? So intentionally I put a 0 at origin, and there is no 0 at origin among the poles. So at very low omegas, I start from 90 degrees lead, and eventually I start to lag and settle at minus 90 degrees. And roughly, I think it is kind of possible to see. I have a feeling that something is happening roughly at as 0.1 hertz. Is that hertz? No, radians per second. Something is happening here. The slope is changing. About 1 radians per second, something is happening. That is my resonance frequency. And so that is probably one of the poles of the system is close to that. And finally, I reach to minus 90 degrees lag. Okay, that's all I have for now. Let me stop this. Camera only. So this is Bode plot. It is very useful to visualize how the system response changes as a function of input frequency, just by showing the amount of gain and lag. We essentially know everything about the system response. And also we see how we can use some information that exists in the Bode plots to infer something about the properties of the actual system that was underlying these Bode plots. So that is, I think, the end of frequency analysis and also the transfer function. What we will do next is open a new chapter to discuss another kind of notation, if you will, way to describe a dynamical system and the analyses that are associated with that notation. That is called state space representation. So until then,